So, some quick context for this video. I was looking through some of my notes, and this formula popped up a lot. And at one point, I understood it. Like I truly understood it. I was able to derive it, but I've just been MIA from programming because of life for so long that I kind of forgot, and I didn't have notes on this, like on how I got there. Oh, my bad, alarm. That is awful. Anyways, so this is total number of subsets of a size n, and more commonly it's used for subarrays of an array size n. Gauss's method was the one I remember learning in class, but it wasn't intuitive for me. And the reason I'm harping on intuitive is that, like, let's pretend a interviewer asked me how I would derive this. I have like a BS method of like going around that, where either they hit me with a follow up or they wouldn't hit me with a follow up. And it's like, well, I know that all possible subsets is n squared. And sometimes you get a problem that is looking for pairs, so you can get away with a non contiguous one, and that's closer to n squared, because the only one that it's not going to include is the empty set. Empty set is like rarely an accepted solution. It depends on the constraints of your problem. But then there are other times where even these don't make sense. Like if you're looking for a total sum, a running sum, a product sum, then your problem usually has a contiguous answer within it. And that's a lot closer to this formula down here than it is n squared. But my BS solution is always, hey, well, I know that all possible subsets is n squared. Big of O is the worst case scenario, the upper bound. So if all possible subsets is n squared, then my solution is always going to be bounded by n squared, thus O of n squared. And even if I go down here, n times n, we're going to get, n squared plus n. So that's how I would usually kind of like just BS it. And sometimes they'll take that, sometimes they wouldn't. But this visual proof that I keep going up and down on kind of already follows my line of thought, and I thought it was super fun. So let's start with the problem. I picked like a small enough problem where it's not annoying to write. So let's do an array with 4 elements, 1, 2, 3, 4, right? Plug it into the formula, we should have 10 subarrays. Cool. Let's write them all out. 1, 2, 3, 4, all the pairs, all the triplets, and then the array itself is also a subset. So we have 4 singles, 2 doubles, 3 triples, and then the whole itself. And that adds up to 10. So it checks out. It's very consistent. But I still don't understand this. Like, how did I get there? Well, this is where the visual proof comes in. We had 4 singles, right? Let's pretend this is like a grid and just start plotting them all out. Right, we got 4 singles, that's our base right there. We got 3 doubles, 2 triples, and then the whole. And like I said, my brain immediately goes to O of n squared, so let's just complete the grid. Let's just complete it. N squared, 4 squared, 16, ready to go. Let's just complete it, right? We have data that works, and then complete the rest with like emptiness, like that doesn't exist. That we don't really care for our problem or the context of the problem, but it's still there regardless. So this is the upper bound that my brain is like immediately drawing. The diagonal is always going to be n, and this is it's somewhat intuitive, not truly intuitive for me, but it's fun to visualize, and I know I can get to it after I learn it. But the idea is, if this whole grid is n squared, and we know that the diagonal is n, what if we take out the diagonal? If we remove the diagonal, the remaining space is going to be, remember, we had n squared, the diagonal is n, so we have n squared minus n. And then it looks a little something like this. And what's cool about it is that now we have 2 equal triangles. We have like the upper side with like a bunch of non-existent space, and then the bottom side that has like all of our solutions or potential solutions within it. And this total area with the diagonal is n squared minus n. You factor that out, what do you get? N times n plus 1. So we have half of the problem already solved. And speaking of halves, because we know that this total area is n squared minus n, and that it's perfect halves, if we ignore the white space up top, that leaves us with just the bottom triangle, which is n squared minus n for the total, divided by 2, because we only care about the bottom half. So now we have n squared minus n divided by 2. But, you know, the diagonal still has data we want. It has the data that we wanted. So let's just add it back in. So now we have the bottom triangle, n squared minus n divided by 2. Add back the diagonal. Now do some arithmetic, you know, make the bases equal to n over 2. Then you get n squared plus n over 2. Simplifies to n times n plus 1 over 2 for the possible combos, all possible subsets, which is a fun visual. It blew my mind, and I know that, like, after some time, especially after making this video, that this is probably something that I can dedicate to memory, and if needed, even like draw it out for the interview, or like maybe post interview, or like after I get the solution, because like I promise, because sometimes we get like a big time crunch. So let's go back up to Gauss's method. Gauss has this interesting method where he gets the whole infinite series, then he reverses the infinite series through what is that called? It's like a law of mathematics, and I completely forgot. It's where you can flip around all positive terms, not positive terms, but all terms. You can move them around, and the solution's still the same. Well, that's what he's applying here. So it goes 1, 2, 3, and it goes all the way to the last element, which is n minus 1, n minus 2. Flip it. You know, it's at the same time, it could also just be n minus 1, n minus 2, until you make it all the way down to 1. So let's add those terms together, right? Let's add them up, because then it's just going to be summation plus summation to summation. But add them like the original, but to the reverse version of it. And what do we get? We get n plus 1. Cool. Now we get 2 plus n minus 1, which is also just n plus 1. We get 3 plus n minus 2, which is also n plus 1. So our solution is just going to be a bunch of n plus 1s. But how many of those do we have? Like, if you think about it, right? We have n of them. So instead of writing out n plus 1, 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 we can just say there's n plus 1, so n times n plus 1. And now we have this. 2 summations is equal to n plus 1. Well, just get rid of the 2 at this point, but equal out the sides. What is summation? Summation is n times n plus 1 over 2. This is cool. This is cool. I remember learning this in school, and it was like, I like this solution, except my brain does not immediately think, yo, let me reverse the series and add them together to get the proof that I want. That's Gauss level genius. I am not Gauss. I do like drawing. I do like visuals, and doing diagonals and triangles is a little simpler for my brain to comprehend. But you may not be convinced yet. You know, it's like, okay, but does this work all the time? Because that looks kind of funky, especially if you haven't touched math in a while. Like, how can I trust this? Best proof I found is just from my discrete notes, you know, proof by induction. So you hypothesize that the next step will work. So let's start with the formula. You know, we know that n plus 1 is over 2. So that's just going to be like our base proof. Check the base case. Does the proof even work? Pick a number that is easy to work with. N is equal to 1. Plug it in. Is 1 for n1 equal to 1? It is. Cool. So the base case works. Now this is where the induction hypothesis comes true. If we make it a constant, if it works for n, it'll work for any constant k, right? K plus 1 over 2. Now this is where the induction step happens. This is where we assume, because it works for k, it should work for k plus 1. And if it works for k plus 1, then it should also work for k plus 2, because it worked for k plus 1. And the way you prove this is by just plugging it in. So if it works for k plus 1, if it works for k, it should work for k plus 1. So plug in k plus 1 wherever you see a k. We see a k here, k plus 1. We see a k here, k plus 1. Plus 1. And this one, it doesn't feel like a proof because it's so straightforward, because you can visually see that the formula is right there. You can visually see that it's right there. But let's pretend it was like this, right? Well, let's pretend it was looking like k plus 1, k plus 2. You can factor them out, factor out the k plus 1. Not factor it out, but like break this apart. You can break that apart to make it look like k plus 1 plus 1. And that's usually where like the mathematics, having an eyeball for it and trying to get to this usually works. But once you see this right here, that the k and k plus 1, once you see that this matches up with the original formula, it's proven, because reasons. Proof by induction wasn't my strong suit. I just know if you can somehow get the arithmetic to match the original one, it will work. And then you can do the same thing for k plus 2. So wherever you see k plus 1, put a k plus 2 in there. And it just keeps proving itself. I'm not too sure if it goes to infinity. Maybe all natural numbers. But to be fair, now that I think about it, yeah, to be fair, it could be like k plus n, where n reaches infinity. That should still work. But even then, your LeetCode problems, like if you check the details of the constraints, you're only dealing with like, what, 1,000, 10,000, maybe worst case scenario, like 1,000,000. N isn't going to be infinite or reach anywhere near infinite level sizes. So yeah, proof by induction proves that this should work for all cases. So if you like the pictures like I do, you can derive the formula. If you have that genius level intuition where you can just sum the reverse series to the original series, then yeah, you can also come up with the exact same solution. You're just a little more genius than I am. And then you can do proof by induction or forget another proof. Maybe you could probably do this by like proof by contradiction to convince yourself that this will work for all cases. But man, no, that was the video. I think I want to try doing videos a little more often than just completely writing out the blogs, because the way I have my program set up, I have to edit a markdown file for each blog post, and that was getting kind of tedious, especially managing the folders for like screenshots and stuff. So I'm gonna try out a few more vlog videos to see if that's a little easier or quicker, because I'd rather just get more videos out there. Because I go months without touching my blog, like literal months. I got the website up, I did one LeetCode problem, and then I just disappeared for a while. And I feel like part of the reason is like that. Oh, dude, I have to do so much work for such a simple blog post, and then the writing is crap because I want to go in super detail, but at the same time, I don't want it sounding too verbose. Here, I can just rant, have fun with it, no script, and just fly through it. Fly through my notes that I did earlier. But yeah, that'll be it. I'll see you guys next time.